Next speaker is Davide Villa, CRO of XINNOR. And he's going to talk about all-flash, multi-node, high-availability, disaggregated implementations.
Hola, hi everyone. My name is Davide Villa, actually David Villa in Spain, the famous football player. I cannot play anymore, so I need to earn my money. Today I'm going to talk about storage. I'm going to talk about high-performance storage for HPC and even more for AI workloads. Before doing that, let me introduce the company because I guess many of you don't know who we are. So we're still a startup. We were founded in 2022. We focus on developing software for a high-performance storage. And more specifically, we focus on the data protection. You can call it RAID, you can call it erasure coding. What matters is that we protect data from drive failures or even server failures. Trust me, we're super fast, but don't trust me because I'm in sales. You can look at the IO 500 results, and actually next week at ISC, the new IO 500 list will be published, and spoiler, we will be on the podium of the IO 500 for production level, so it's not just research, real deployments through one of our major deployments we did at a university in Germany. So why do we need a new data protection scheme for AI workload? So you're coming from the HPC space, and now I'm pretty sure most of you are exposed to AI projects as well. Can you use the same tools that you were using on HPC also for AI? When I ask people like you, what's the workload on AI? The feedback I get is that they don't know. They need to provision for the worst. They know that they need not just a sequential performance, sequential read, which is very typical on HPC. There is a mix of write, which really matters for checkpointing, and it's not always a sequential write. It's also a combination of random write, random reads. So it's a very complex workload, which is ideal for Flash. Now, if we look at Flash on its own, they're super fast. So if you look at PCIe Gen 5, today you can get 14 gigabyte sequential read. You can get multiple millions of IOPS from a single drive. And this is valid for almost all the SSD vendors. But then when you look at the system for AI, and I'm just quoting one which is very popular in the market, taking the number from their website, you see from a system with up to 56 of those drives, they get the performance of only 3 drives in sequential read and not even 1 drive in random performance. So why is that? There are 2 reasons. One is the data protection scheme that they use, and the other reason is the file system that they use. They use NFS, and NFS is notorious for poor random performance. So what we tell to the customer is that what you have been doing so far on the HPC is still very valid. So you are very familiar with parallel file system. You used to run Lustre, BGFS, GPFS. You don't need to change. Those are, they come with a lot of features, security, and also usability, experience that you gain over the years to use those file systems. They're still very valid. What you need to do is a high performance drive, NVMe flash, and the right way to protect those drives, because traditional methodology to protect SATA and SAS HDD or SSD cannot keep up with the performance of the SSD. That's about my sales pitch. Now let's go into the technical talk of what I was supposed to present today. Clustering, how do we protect? First of all, what is clustering? So You want to implement high availability to protect in case not only a drive failures, but also a server failure. And what you want to happen in case of a server failure, you want to have all your data available, and you don't want to face a drastic reduction in the performance. You can do this with mirroring, replication of the data, but mirroring is super slow, and it's expensive because you need 2x the amount of storage. Or you can do with clustering. And if we look at typical clustering implementation with Lustre, but also with a BGFS, it's made on pairs of server nodes. So you have 2 nodes in a cluster, which becomes a building block for the overall cluster. And normally those nodes, they share the same drives. How can we implement HA with NVMe drives? There are 2 ways, and that's valid for any software hardware RAID protection. So there are 2 ways. You can use a storage bridge-based server, 2 server nodes connected to share NVMe drives in the same box, or you can use EBOF. EBOF are Ethernet attached, just a bunch of flash. So it's a very long acronym. Basically, those are boxes with a lot of NVMe that connect through NVMe over Fabric through TCP or RDMA, or Ethernet RDMA. So the way it works when you have those 2 nodes connected to shared drives, at the beginning, we connect all the drives to each of the 2 nodes. We connect them by creating namespaces, 2 namespaces on every drive, so that we can maximize the performance. And in normal operation, you have some RAID groups for metadata and for data on one node, and some other groups on the other node. In case of failure of one of the 2 nodes, we can fail over all the RAID groups to the other node. And then in case the node is back up, we can fail back the original RAID groups. So very simple. There's no magic. We do that with a pacemaker and CoroSync, and that's the typical implementation with parallel file systems. Now, what we need to be careful about is what happens in terms of performance. Because when we failed the RAID to a single node, when previously we had 2 servers running that workload, and now we have a single server. So we need to provision that server in such a way that when it will be taking care of the fail node, there's no performance degradation. And that matters because you might think, okay, it's just 2 servers, I don't care. It matters because if you slow down one of those building blocks, it will slow down your entire cluster. And that's very typical with Lustre, but also with BGFS. So let's look at how to build it with storage bridge base. With storage bridge base, we have this limitation that each NVMe drive has 4 PCIe lanes. So to get the maximum performance, we can only connect to 2 PCIe lanes per server. And to get a maximum performance, what we do, we split the drive in 2 namespaces so that we have virtually 48 drives that we are running on. It creates some additional complexity because of that, because of the need to manage more namespaces, but it's a very elegant solution. It's a simple solution. It's just 1 server, 1 box, which provide high availability. The challenge with this implementation is that there is no way to avoid performance degradation. When you lose 1 node, you connect only by 2 PCIe lanes to the drives. So you still have all your data, but they will run 50% slower than before. So with EBOF, is that different? Yes, that is different. EBOF, normally they are just a JBOD with NVMe drives with 2 I/O modules for redundancy, and you can have 3 to 6 network cards with different performance speed per network card per I/O module. So in this case, you can connect two servers directly to the eBOF, or you can go through a switch. If you want to build something which is really HA, you need two switches so that you don't have a single point of failure. What's the advantage of this architecture? While storage bridge-based server, they are only offered by a limited number of vendors. In this implementation, you can use any server. You can use Lenovo, HPE, Dell, whatever server vendor you prefer to use. There is no need to create multiple namespaces, so there is no complexity in managing the NVMe drives. There is no limit in the number of drives that you can have because you can attach multiple eBOF in the cluster. You can avoid the performance degradation. So if you properly set up the network connectivity between the server and the eBOF, you can avoid the performance degradation. Still, if you have two servers connected to the eBOF, the server that will survive will need to be powerful. So it will need to be provisioned with 2x CPU capability, with 2x DRAM. So it's still not the ultimate solution. So why not building a multi-node cluster at that point? So with Pacemaker and CoroSync, we can do it because they support up to 32 cluster nodes. With eBOF, we can do it because we can attach as many eBOF we want. And in this case, we focus on Lustre. Lustre supports multi-node clustering. So how does it look like? Multi-node clustering, you can have multiple active servers with metadata and OST connected to multiple eBOF in the cluster. And then what we recommend is to have a standby server in case of any of those servers going down. So in case of failure of one of the servers, all the RAID groups will be migrated automatically to the standby server. And in this case, there is no performance degradation anymore. So you still have all your data without sacrificing the performance. Obviously, it's a bit more complex architecture to implement, but we believe it's the ultimate way to get high availability without performance degradation at scale. If you don't have scale, SBB, it's a simpler type of implementation. So the big benefit of this implementation is that we eradicate the performance degradation on the solution. We're a very techy company, so we built all the reference architecture on how to implement high availability on SBB, on eBOF, single, dual node, multi-node. There are step-by-step instructions how to set up with Lustre and with BGFS. We also have in the pipeline a paper for IBM Scale, IBM GPFS, which use a different type of HA implementation. So I encourage you to look at our website, at our blog post. There is a page with blog posts that those are very technical documents. So as a conclusion, so what we see, I'm sure you see it more than myself, with ML and AI, you need more faster storage. You're spending so much money on GPU, you don't want to keep your GPU waiting for the storage. And to get higher performance, you need to deploy Flash, but Flash are a bit more complex to handle when it comes to data protection than traditional HDD media, simply because they go faster. And when you go faster, you need to be able to cope with your checksum calculation to avoid becoming the bottleneck in front of your Flash. So data protection really matters, and that's what can really make the difference in terms of performance, reliability, and cost optimization. And don't trust me again, prove it yourself. It's a software, so if you want to play with the software, You just go on our website, you request a trial license, and you can play with the software. That's it. Thank you.
Thank you so much. Any questions? Okay, one question from my side. So do you have any bus buffer technology implementation?
No, because we deal with NVMe drives. So NVMe are pretty fast, so we don't have any cache implementation in our architecture. So there's no cache and no need for any bufferization.
No, it's bus buffer. It's more on the allocation. So usually, imagine a solution that's very, very fast. You don't want to expose this to the complete community or the complete user base using the cluster at that time. So maybe you want to expose just this particular capability as part of a job complex workflow, and then you use Slurm or any other workflow manager that can kind of spin up this and allocate this particular set of storage for a particular job.
That's more a question for the file system itself. Yes. Because we sit underneath the file system. So we provide that layer of performance, and then it's up to the file system to provide a multi-tenancy or provide any partitioning, anything like that. Okay. So from our software itself, we don't.
Okay. So well, thank you so much.
Thank you.